So for this project, I wanted to design a isometric 2D pixel art kind of house layout, as seen in something like Stardew Valley, where we have the wall rendered, we have the roof tile trimmed here, we also have ability to place objects, and we also have the floor tiles. So we have all this information here, the corridors, and so on and so forth. And we should be able to create something that kind of looks like this within our project. For now, I think we'll have it without furniture and just have the tiles and just the kind of layout formed. I think having furniture that just extends the complexity, and it will be needed for a different video, because maybe we can look at also procedurally placing objects like beds and stuff in a realistic sort of fashion, which would be quite fun. So what algorithms out there are there that we can use? Well, I've been trying out a few before we start this video, and one I found was this one from the Emergent blog called a dungeon generation from simple to complex. And this was kind of an idea of you had a box and you simply started randomly placing the boxes next to each other and so on and so forth, and you kind of got this roomy kind of thing. And the more you go, there's going to be gaps in it and so forth. And I did give it a go and implement it because it was very simple. Just give it an area, place blocks within it, and there you go. And as you see, this is the results. They're pretty interesting for a dungeon, but for a room house layout, that just doesn't make any sense. They're just kind of randomized, jumbled mess. And in some instances, I had it where they were just long lines. So this is good for a chaotic, kind of like a cave. If you think about a cave is very disorganized, something randomized, more stochastic. This is far better. As you see here, we get rooms that aren't squared. They're just of different shapes, but being easy to manage. So still cool, but not what we kind of need. Really, the next logical space was to use a sort of space partition, which is also used in dungeon generation. But as we look in the early iterations, in about the third stage, we get these nice blocky outlines. We don't need them. We don't need to produce smaller squares within it. We just need this one. And we can imagine that the dash line here is actually just walls, and we can just simply have gaps in them or doorways, and that would make for a pretty decent house layout. And so that's the first part we're going to do. Binary space partition is really simple. We're just given a space and we just simply randomly split it in a certain direction at random. That's really it. And then we can either split it horizontally or vertically and so forth, depending on which has more space. And eventually, after so many iterations, as you see, 4 splitting iterations, you end up with something like this. That's really quite nice. And if we keep the iterations very low, and if I run it here, this is the kind of results we get. We get here kind of a decent house layout. I've highlighted the areas like the actual room and kept a pixel space here for like what we consider the wall, and we have what we consider like a 2-bedroom house in this case, like the ground level, the floor, where you could have a kitchen, the lounge, a dining room, and a toilet, for example, within this small confined area, which is pretty cool. But to quickly just go over the code, it's actually really simple. For a binary space node, there is some redundant code that we can ignore, but really for a room, we just need the X, Y, the width and the height. And then you could attach extra details that will come important later. But some of these kind of experiments, I've actually left them in. So you can think, for example, I was testing out an exterior side, so which is a room that is at the edge of the house. So you could have windows there, for example, or an entrance. That was also a boolean here. So the entrance to the house, but they can come on later. Let's just look at the space partition. For the actual binary space partition node, well, we contain the room that I just said, and then we also have a left and right, which is just a reference to another node, and we can have it as is a leaf. When we refer to a leaf, we can think of it as a tree, because that's kind of what we're making. We're making like a tree graph. We have the branches and we have the leaf. Imagine the leaf as the actual room with all the details, and the branches just sort of the connecting the wall kind of parts that we're looking at. That's it. They're just the connections. So when we actually want to generate our binary space partition, we first just give it a root, which is the width and height of our area, and start at 0, 0 to the top left corner, and then we can just split that node. And when we split our node, we can just do some checks. Are we actually capable of splitting? If the iterations are 0, so we're done, and we return it false, that's the end of the split. Then we can choose our split direction, which is just simply based on the certain things. So if the width divided by height is greater than 1.25, then we split vertically, else we just split horizontally. If for whatever reason that can't happen, we'll just pick at random. Or you could, in obviously a lot of cases, because it's very customizable, completely organize this and just choose at random. And if it works, let it continue. If it doesn't fit your specification, you could retry and choose the other option. So there's a lot of customization you can do. We have our split direction, we just check over the if statement, give it a randomization to it as well, and then we have our node left. We've provided a new node, which is its new x, new y, its room width, and then its split position, and we do it for the same for this one, and we do it for like the opposite side, so the negative and so on and so forth. And it's just the same for this one, except obviously we're just doing it now on a different axis. And once we're done, we obviously declare that this one was not a leaf, it is instead going to be a branch, and then we continue it with the iterations. We just take one away from it, and that's it. That is the code essentially, and that will eventually give you a binary space partition after so many iterations you set it as. When we actually want to analyze our node, our binary space partition, we can just simply recursively go through it. Because it's not a traditional array, we can't do a simple for loop. In this case, we give it this function that goes through and it says, hey, if this is a leaf, then we should just process it and do what we want with it. So i.e. in this case, I'm creating those red squares as mentioned. If not, then it's a branch, and therefore we should pass in the node.left and node.right into the same function. So we're doing recursively, but it keeps going until, well, we hit the end of it, really. That's it. There's no more leaves and branches left. So cool, simple. We get a nice little layout. Let's add some more detail to it and customization, shall we? If we refer back to the Stardew Valley image, we notice that there are room types. So we can have a bedroom, we have a sort of living room, we have a kitchen which has tiled floors. We also have like this spare room, and we also have the children's room. So at one point, we need to be able to determine what kind of room is each. So an entrance wouldn't really go to the kitchen, and the bedroom wouldn't be connected to the kitchen either. It'd be connected to the living room is here, and the living room would be connected to something like a bedroom or like a corridor and so forth, or a spare room. You wouldn't have the children connected to the kitchen. So we need to have that logical sense when we generate a house layout. I'd like to read up a couple of academic papers on this. So this one, a constrained growth method for procedural floor plan generation. If we scroll down a bit and we see what ideas they came up with, they have this where it has a private zone and a public zone. A private zone consists of things like your bedroom, your bathroom, your toilets, while a public zone is your living room, your kitchen, your dining room, or like a landing area that's accessible to the public. So you'd all meet in there, you wouldn't all meet in the bedroom, for example. There was also this one, which is a novel algorithm for real-time generation building floor plans, and this one had the idea of it's like a hierarchical method. So it goes from the outside to the living room, then it goes to the bedroom, master bedroom, kitchen, and so forth, and has this order. And it tells you how it goes through. I didn't all use them because obviously some of these get very complex. So this one, in fact, I believe uses a pathfinder to then place like the hallway and so on and so forth in order to make logical sense. But there's a lot you can learn of how it works. So the corridor placement, we see that it has like a formula to do it, to where it should go. And I think for me, there's a balance between it being too complicated and it being to what we want, our expectation and our satisfaction. So for my example, I made a bit of a compromise by having some places sort of hard coded in. For example, the hallway, I will just decide where the hallway will go without trying to figure out where it should be. So between both the public zone and the private zone, there is a hallway. And we can see the top one would be considered the public zone because we have a nice big living room, and then we can have things like the kitchen, a dining room, and then possibly a toilet is here as well or nearby. And then for the private zone, we can imagine one is the bedroom and then also an ensuite bathroom, for example. The green squares, as you can imagine, are just the doorways between them. And you notice we have this really quite nice connectivity. So it goes from this room to this room to this room to this room. But to actually make this layout, we just need multiple binary space partitions and just split each section we want. In this case, I just hard coded. So for example, the public route, it just starts at 0, 0, and we take up this much space, and we have this many iterations. I'm also converting these to array for later use, and we can do it for the hallway. We don't necessarily have to do it for the hallway. The hallway can just be that gap, but I thought I'd just keep it consistent and allow for modification. So you could do a hallway that's split up into two, and maybe the hallway at the end is actually a bathroom, for example. But if you give it an iteration of 0, it obviously just doesn't split, and it'll just be that square area, that one single leaf. And same for the private route, it's just the same thing, but we have less iterations, just 2. To actually establish the room connectivity, we can just simply check where the next room is. So in this case, we store the last room, and we just find which edge it's connecting to. And once we find the edge, we can just simply place a door at random within a range. And we have the +3 and the -3, so the door will be of a height and width of 3 pixels, and therefore, or 3 tiles, I guess. we don't want to have them too less. If we have them too little, then it will cause it to overlap with the walls and it won't make any sense. So rendering the inner room and the walls does get a bit complicated, because when we think about it, there's the width and height of the actual leaf, then you have the width and height of the room itself, because we got to think of the wall. And so when we have these process functions to process the outer edge and then process the inner wall, the outer edge is just take away 1 from it. And then for the inner wall, so we have the wall on this one, and then we have the inner wall is going to be -2, so it just gets a little bit complicated, and that therefore this one needs to be 1. So when I run it, in fact, you can visually see it, that we have, here's the edge, and then we have the wall, and then we have the inner room itself, the actual room. This is just so we can display it nicely like this. This will change when we have the actual 3D renders, or not the 3D renders, but the actual tile set used. It should be important to note to also free memory from this. When using these binary space partitions, because we're referencing a lot of memory, we do need to free it. To simply free it, we go through recursively by just simply freeing the node. Otherwise, you will get memory leaks that way. So how do we determine the hallway connectivity as seen in this one? Now we have the hallway connecting to these 2 looking big rooms. Well, we can decide it based on the room type and assign a room its type. So I kept it incredibly simple. To assign a room type, you're simply just deciding it based on the size of the actual room, and we sort it by that size. I'll just use a quick sort. Probably better to use an insertion sort because the arrays are so tiny. And when we do that, we can have certain types. So because the largest room will be organized first, we can set that to be a living room. Then the next one can be a dining. Then the last one can be a kitchen. And then for something like a private, we have the big one, then a bathroom, and then we consider the smallest one as a wardrobe. This seems okay, but there's probably significantly better ways of going about this, because there can be instances, if I, for example, run this and hope for it, here, when we have the public room, we have them 1 by 1. So you could, for example, have a living room, then a dining room, then a kitchen. Would that make much sense? Maybe not. So there's something like that where maybe they don't make much sense, but again, how deep and complex do you want it to be? I think this could be okay. It'd be functional. This makes it, for the hallway connection, just pretty simple, because we're just doing the same thing we did with the door connection, and we just need to check what we simply can just loop through the rooms. And because the rooms are sorted, we actually don't need to specify the type for now. Maybe we do later, and we just simply check which side it's next to, and then we can just randomly place the doors. And we do it the same way. That's it. We place the door and we give it the tile index 2. So that when we run it, it'll always be the first room that we have, always the biggest room in this case. And so you can imagine this is the bedroom, and then that would be the ensuite bathroom. This is the living room, all connected via the hallway. Having the door randomly placed perhaps does not make sense. Doors aren't really randomly placed when you think about it. They're usually placed in strategic positions, or either in the center or in the corner or the edge, for example. Usually next to the wall. So you open the door, it's next to the wall rather than it being in the center of the room, for example. It's always in like a corner. So that's kind of cool. Let's add some actual tile sets to it. Let's add some bit of stars to it. Let's add the roof trims to begin with. So when we run it, here it is. We can see that we have those roof trims as seen, like in the Stardew Valley example. We have it here, they look nice. This is like the top of it, looking down there, and we have the black space of the actual space. We also have the doors open as well. Now, as a prerequisite, you'll need to have a bit of knowledge on how auto tiling works, and luckily for you, I have a whole video covering auto tilers in Odin and Raylib, and I'm using this, in fact, pretty much the same code that I've used in that, which is a free GitHub repository that you can also use here, and I have other links. This is just a way of using different type of tile sets, such as edge, corners, and so forth, to make things like this, and is used in the room generator. But we don't need to change the actual generated code. We just need to apply our array to our auto generator to create the bisque mask, and we'll use the grid, and then we'll just leave the floor for now. The floor will be our floor tiles, as in the name, and the grid we can imagine as the roof tiles. I'll also get into explain how many sort of arrays and types you'll need for later in the late stages, but we're just trying to demonstrate it. So we'll use the bit mask generator, as I said, and again, watch the video or look at the code if you want to understand how it works. And we just simply loop through our array and we provide it, and we want to ignore our 15, or because a 15 is when all tiles are surrounded, so it should be a full one. In this case, the roof trim, unless it's transparent, we just ignore it, and that does give us our nice open area where we can start rendering things. If I actually ignore this, and I'll show you what happens, this is what it will look like that, and do that. And if I run it, there we go, that's what the fill space, and that's because when we look at the images, we can see that 15 is when it's completely surrounded. But in this case, we just want to ignore it. So let's take a big leap and go to adding the floor types. And so when I run it now, boom, look at that. That looks pretty cool now. We even have an entrance as well leading to the house. We have carpet to represent something like a bedroom. We have tiles for something like a toilet or a bathroom or kitchen. And then we also have one for the living room, and maybe the dining room could be like a wood floor, which is pretty nice. We also have the nice walls rendered as well, as seen as well. So everything's looking nice. It's looking like that Stardew Valley example I showed you. So how do we render the floor? We have a wall, and then we also have the floor. Well, for the floor, it's really simple. You just need to determine how high you want the wall to be. In this case, this is 3 tiles high. So a wall is 1, 2, 3 tiles. And that means when we just simply check in our loop, we just need to check if it's greater than or equal to +3 of the current room.y, and therefore we can place the floor tile. And because we have the tile type, we can also determine what floor tile should be. If it's a bathroom, we can have the tiles to be 3, and if they're not, like a bedroom, they can be carpet, else we just default to this value as set below so we don't override it. We can check in the trimmings here where they are set, and so when it comes to men, we just simply give it that. There's probably, well, there is better ways of determining it, because if we look at our house gen again, how would you know this? You could probably use an enum and say this to be tile, for example, which would make more sense, and you can still use it with the generator or just whatever. You just need to make some modifications. And that means when it comes to actually looping through and doing the walls, we can see we can just set it as a 2, as that will be the wall. If it's less than 3, and if it at least equals 3 as well, then we will place it like that. This just does get quite messy with all these different checks to come in, because there are certain situations that are unique to it. For example, when we're doing a doorway, we need to determine if it's vertical or horizontal, because we place the trying to keep it all within the one function while trying to reduce the amount of loops. So we're going through place all the walls, and so when we're adding the doors later, that means and when I run it again, if there is a door here, for example, or there's going to be a wall here, that means we need to determine if we should remove that section and then place the floors. Or if it's like this, then we need to place the walls, for example. But with our doors, we can obviously determine if it's vertical or not. We simply set it as false, and we can just give it. So if it is vertical, then we do in the normal traditional way. If not, then we do it less than 2, and this is because of the way the auto tiler works. Obviously, it's has a width of 3, but actually comes out as 2 because of the way it works, the way that tile set works. So that results in checking out, and then we just simply press it 1, and that will remove it, and we add +2 because that's the height of what we have, including the current Y. Pretty cool. When it comes to assigning the room, I make a bit of a change. I was using quick sort to just sort the array and then return that sorted array. In this case, I didn't want the array sorted because that can break the tree flow. Not always that the first in the tree, it's not going to be the biggest room. That's not always the case, and therefore if we do sort it, sometimes we lose that door connectivity. You could sort it and then just rerun the whole thing again, and so on and so forth. But I wanted to reduce the amount of loops to happen, otherwise it kind of gets excessively kind of inefficient to constantly loop through the same rate when it could be all done within the one, and we want to try and reduce that. So when we just assign the room, we just simply create another array that just contains the size and then the index, and then we just loop through, and we can determine the index and then assign the room like that. This is far better to loop through what, in some cases, the array is going to be the size of 3, so tiny, so easy to sort. By adding an entrance, I kept this super simple, but you could add more variations, just like which side of the entrance should be added. But in this case, I just simply check for the hallway. I just pass in the room I want to have an entrance with. So it doesn't necessarily have to be the hallway. You could be like a landing area, for example, or even like a kind of a living room. You know, you don't necessarily have a house where you just walk in, it's the hallway. It could go straight to the living room or to the stairs and so forth. In this case, it's just simply the same as the hallway. Just find which edge it's on. In this case, we actually need to check if it's 0 because we're dealing with the exterior, or if it deals with the width. And we can place the door randomly, and we do the same similar checks as before. Check if it's vertical, check if it's not, with some slight variation. You see, it's getting a bit finicky when it comes to that because we need to check for all the different types of possibilities. When we look at it, there we go. We have our hallway. You see, it generates at the bottom. Now, there is some slight bugs that you may want to fix, well, you probably should fix, either make it impossible to happen. So we see here that when we generate this wall, it's a tile set and it's doing the auto tiling thing. So it's checking all nearby neighbors. And so that means if we have a wall tile set, like a door hallway, that's very close to it, we can see that it knows it's the corner and it should try and do something. But in the actual trimmings tile set, it's not possible. There's not enough combinations for it. This is the only amount of combinations there are. Therefore, this result is actually impossible to do. So you actually, perhaps when you do a generator, you want to have some exceptions and to ignore situations like this. To ignore, for example, a corner piece in this situation, or you set it so that the height where it can generate, it just doesn't happen. It can never collide like that. But it may be that you want it, like that for your situation, depending on how small the rooms are. Another change we can do, when we looked at the binary space, we were splitting it to 2 different rooms. Well, in this case, we should probably want to reduce it to just 1 split. In this case, I just choose at random which one it should split at, and pass in the iterations. And the reason to do this is because if I want 4 rooms, I should just be able to pass it in 4 iterations. So if we do 3, I should be able to do 4, for example, with a public room, and we may get 4 rooms. And I say may, as we see here, 4 different rooms with all nice connectivity. But I say may because there's going to be a minimum size that we want. And for us, the minimum size is obviously depending on the doors as well, because we are doing +3, -3 as well. So it needs to be at least 3. And we can set it here up the top. You can also set a max room, but it doesn't do anything. I left this in by accident because the max room breaks the split. If the first split is going to be like too big because the room's too massive, and therefore it's just never going to split. So we at least want a minimum room split of 10. So if we do too many, I think even just 5, it will struggle to do 5 because they're quite big. 10 is quite big out of a 50-50 space. There you go. We only got 4 about that. And so with this, we can experiment a bit. Here's a more, I would consider kind of a small house. You just have a nice corridor with the entrance. You have it going to the living room, and then you have it going to the kitchen or dining room and so forth. And you can just simply randomize it as seen here, where we now generate the house with the width, give the width 5, and we randomly choose between the previous house we did or the normal one with the corridor in the middle. And we can also change the ratios, the space between them, as done here, generate normalized random. We can do some nice code cleanup, and rather than just return a bunch of arrays that we have the values, we could probably have them in an object, a structure like this, where we have the house and its house layers, and then each corresponding array, so the floor, the roof, and the wall, and then objects would be your furniture. It's just a nice way to organize them. So rather than returning separate arrays, put them all in the same one and then just return it. And so when we go to main and we want to generate our house, we'll generate a house layout, give it the grid width, grid height, and done, and have our bit of randomization. The code is available as always under MIT license, and I have all the different tags for you to check out the different versions. So version 1 is where we start from, and then version whatever is the latest one at the end. I'll just end it with, come along and do subscribe and like my videos. I have other interesting videos that I cover, particularly with procedural generation, such as paths, even procedural music most recently, and of course that auto tiler that I mentioned, and other general videos. So I look forward to seeing you there in future videos. See ya.